What happens when an interviewer wants to see if you can beat the sort and pray approach? KTH largest element in an array is a classic efficiency trap. It looks easy, but the real test is whether you can find the answer without sorting the entire array. Nail this and you prove you understand heaps, selection algorithms, and performance trade-offs. Let's attack KTH largest element in an array with a basic problem-solving framework. Breakdown: given an integer array nums and an integer k, return the KTH largest element in the array. Important: it's the KTH largest by order, not the KTH distinct. Example: input nums equals 321, 5, 6, 4, k equals 2. Output 5. Largest is 6. Second largest is 5. Real-world example: think of a leaderboard system that needs to show the top k performers, or a monitoring dashboard that wants the KTH highest CPU spike without sorting everything. Classic interview extension: how would you do this if numbers are streaming in continuously? Hint: min heap of size k. Assess what's tricky here? Naive approach: sort the array descending and pick index k1. Time: on log n. Works, but overkill. Better approaches: the interview expects one of these. Minute heap of size k. Most common plus interview friendly. Keep only the top k elements seen so far. The heap's smallest element represents the KTH largest overall. Time: on log k. Space: OK. Quick select: selection algorithm partition like quicksort, but only recurse into the side that contains the answer. Average time: on worst case, on squared, unless randomized. Median of medians: why a heap works so cleanly. You don't need everything sorted, just the top k. A min heap of size k automatically discards smaller elements as you go. Edge cases: duplicates are allowed. And count: k equals 1 max element. K equals n min element. Negative numbers are fine. Structure heap: min heap size k. Plan: create a min heap for each number in nums. Push it into the heap. If heap size greater than k, pop the smallest. After processing all numbers, the heap top is the KTH largest. Return heap top. Approach: sort. Time complexity: on log n. This line imports Java's utility classes. In this case, we need it so we can use helper tools like arrays.sort. Small pause: this defines the solution class. As usual in Java, all our logic lives inside a class. This is the main method. It takes an integer array and a number k, and its job is to return the KTH largest element in the array. This line sorts the entire array in ascending order. After this step, the smallest number is at the beginning, and the largest number is at the end. Pause: this reorders everything so positions become meaningful. Now that the array is sorted, finding the KTH largest element is straightforward. Nums.length: 1 would be the largest element. Nums.length: 2 the second largest, and so on. So nums.length, k directly points to the KTH largest value, which we return. This closes the method, and this closes the class. And that's how this algorithm works. It first sorts the array to put all values in order, then directly indexes into the position that corresponds to the KTH largest element. Efficient, simple, and elegant. Test case check: find KTH largest element. Sorting: let's test our function using this input. Nums equals 3, 2, 1, 5, 6, 4, and k equals 2. These numbers represent an unsorted list of values, and k tells us we want to find the second largest element in the array. Why the solution works: we first sort the array in ascending order. Once the array is sorted, the largest elements appear at the end. For this input, sorting gives us 1, 2, 3, 4, 5, 6 from the end of the array. The first largest element is 6. The second largest element is 5. So we simply return the element at index k. And that's exactly what our program outputs: 5. This matches the expected result and confirms that the sorting-based approach is working correctly. Wrap up: so, our implementation is correct. The algorithm successfully finds the KTH largest element by sorting the array and selecting the appropriate position. Simple, accurate, and reliable. Approach: min heap of size k. Time complexity: on log k. This line imports Java's utility classes. We need this so we can use data structures like priority queue. This line defines the solution class. It acts as the container for our method. Here we define the find KTH largest method. It takes an array of numbers and an integer k, and returns the KTH largest element in the array. This line creates a min heap. A min heap always keeps the smallest value at the top. We'll use it to keep track of the top k largest elements seen so far. This loop goes through each number in the array one by one. Since we scan the array once, This contributes the n part of the O(n) log k, time complexity. If the heap hasn't reached size k yet, we can safely add the current number. At this stage, we're just filling the heap. This adds the current number into the min heap. The heap automatically reorganizes itself to keep the smallest element at the top. Once the heap already has k elements, we compare the current number with the smallest number in the heap. If the current number is larger, it deserves a spot among the top k elements. This removes the smallest element from the heap. We do this because we want to keep only the k largest elements overall. Now we insert the current number into the heap, restoring the heap size back to k. This closes the conditional logic for handling heap updates. This closes the loop. At this point, the heap contains exactly the k largest elements from the array. The smallest element in the heap is now the kth largest element overall. We return it as the final answer. This closes the method. And this final brace closes the class. And that's how this algorithm works. It first builds a min heap limited to size k, then scans the array while keeping only the k largest elements, and finally returns the smallest among them as the kth largest value. Efficient, simple, and elegant. Test case check. Find kth largest element, min heap of size k. Let's test our function using this input. Nums equals 3, 2, 3, 1, 2, 4, 5, 5, 6, and k equals 4. These numbers represent an unsorted list of values, and k equals 4 means we're looking for the fourth largest element in the array. Why the solution works: we maintain a min heap of size k. This heap always stores the k largest elements seen so far, with the smallest of those k elements sitting at the top. As we iterate through the array, we first fill the heap until it contains k elements. After that, for every new number, if it's larger than the smallest element in the heap, we replace that smallest value. If it's smaller, we ignore it because it can't be in the top k. For this input, after processing all numbers, the heap ends up holding the 4 largest values in the array. The smallest among those 4, which sits at the top of the min heap, is 4. And that's exactly what our program outputs, 4. This matches the expected result and confirms that the min heap is maintaining the correct top k elements. Wrap up: so, our implementation is correct. The algorithm successfully finds the kth largest element by efficiently maintaining a min heap of size k, efficient, accurate, and reliable. Alright, let's quickly recap kth largest element in an array, one of those problems that looks simple, but really tests whether you can avoid the sort and pray trap. Breakdown recap. Conceptually, the task is straightforward. Given an array and a number k, we want the kth largest element by position in the sorted order, not the kth distinct value. So duplicates still count, and we're only after that single ranked value. Assess recap. We compared the naive approach, sorting the whole array, which works but costs more time than needed. Then we focused on the more interview-friendly strategy, keeping only what matters instead of sorting everything. That's why the min heap of size k stands out. It's efficient, clean, and scales well when k is small compared to the array size. Structure recap. The plan was simple. Maintain a structure that always holds the top k largest elements so far. As we scan through the array, anything that doesn't belong in the top group gets discarded automatically. By the end, the smallest value inside that top k group is exactly the kth largest overall. Implement recap. After setting up that approach, we ran the solution on LeetCode successfully, and everything executed smoothly with no errors. Check recap. We also verified the logic by running the provided examples and LeetCode test cases, confirming the result matches expectations, and the submission passed all test cases. Closing insight. The big takeaway here: you don't always need full sorting to find a ranked value. When the problem only cares about the top k, managing a small top k structure is often the smartest, most efficient move.